So in the second part of this lecture, we will discuss some of consequences of a theorem in topology, the Baire category theorem. So what is this theorem? Starting with a metric space, a complete metric space to be more precise. And consider a countable sequence of subsets of X. If we have the closure of these sets, or the interior of the closure is empty for any k, then X is not the union of the closures. And moreover, the union of the closure and taking the interior of that is also the empty set. So in other words, we cannot write X as a countable union of closures if the interior of these closures is as the empty set for each index k. Well, why is this called a category theorem? We can categorize topological spaces into two characterizations. Well, to define that, let's start with, let's say, the following definition and more general topological space, xt. A subset A of X is called nowhere dense if the interior of the closure is empty. Also, the topological space X is said to be the first category in some texts, they call this meager if X can be written as a countable union of nowhere dense set. Otherwise, X is said to be of first, or I should say second category. Or non-meager. So here is our two categories. Namely, first category, if we can write X as a union of nowhere dense sets. Otherwise, it will be called a second category. And we can restate the Baire category theorem in this way. So a complete metric space is of a second category. Well, the proof is simple. If, let's say, uh, if X is a complete metric space that is not a second category, then, okay, so let us write that down. It must be of first category. Then, according to the definition, we can write this as a countable union, okay, of nowhere dense set. So the closure or the interior of the closure of A sub k is empty for all k. Since the union of this is all of X already, then combining the closure will also give you X. Indeed, what can you do? What you can do is, this is a subset because a set is less or a subset of the closure, but then all sets A sub k are subsets of X. So you have this other inclusion. So indeed, we have equality here. This is not possible according to the previous theorem, because if we have this nowhere then sets, then X must not be equal to the closure of the union according to the Baire category theorem. This one. So this is a contradiction. Therefore, X, a complete metric space, is not of first category. Therefore, by definition, it is of second category. So this is a theorem in topology. So we will not give the proof here. Nevertheless, the interested reader or the interested one can read the proof in the lecture notes. So basically, the proof is by construction and by contradiction. This is not the precise version that we will be using. We will utilize the version of closed sets. More precisely, we have the following corollary. And we also say refer to this as the Baire category theorem. Again, let's start with a complete metric space. And a countable collection of closed sets. Say C sub k. If X can be written as the union of these countable closed sets, then we can find some index k naught. Okay, so this is the set of positive integers including 0, such that the interior ck naught is not empty. And the proof is by contraposition. So assuming the conclusion or the negation of the conclusion, In other words, suppose that for all k, the interior of C sub k is empty. Since C sub k is closed, then C sub k is equal to its closure. By the Baire category theorem, okay, so we have a sequence of nowhere dense sets. X must not be the union of the closure, but this is of course the same as the union of C sub k, since k is closed. And this is the negation of our assumption here. So that's a direct consequence of the Baire category theorem. And we also refer to this corollary also as the Baire category theorem for simplicity. So let's add additional structure here. The following result is so-called the uniform boundedness principle. So here we consider a complete metric space X. And a norm vector space Y. Also, let us consider a collection of continuous functions from X to Y. Then, if this is pointwise bounded, in other words, the collection C is pointwise bounded in the sense that the supremum of the norm of the images at a particular X, okay, for all F in C, then your collection is uniformly bounded with respect to some ball. So there is some center X naught and there is some positive radius, say epsilon, such that supremum over all X in this ball of the supremum over all functions F in your collection C of the norm of the images is finite. So in other words, if you have a collection of continuous functions from X to Y that is pointwise bounded, then you have uniform boundedness over some open ball. So take note here that for each X you have a different, possibly a different bound. But this theorem states that you can have a uniform bound on some open ball. So to see why this theorem follows from the Baire category theorem, or more precisely, this corollary here, let us take the set C sub k to be the intersection over all functions in the collection of the inverse image of your closed interval 0 to k. Then C sub k is closed since applying the chain rule, you can show that this map from x, now we take the norm with respect to y, so this is now real valued, since this is continuous. And the intersection of closed sets, an arbitrary collection of closed sets, is again closed. Therefore, C sub k is continuous. To be more precise, we should have the argument there. Okay, this one is continuous. For each f in C. Now, given let's say x in capital X, let us consider a sufficiently large integer k x such that the norm of f of x and y is less than or equal to kx. This implies that x is in the inverse image of the closed interval 0kx. Okay. And this is true for any f in C. And why is this the case? This is due to the hypothesis. So existence of kx follows from the hypothesis, meaning if this is bounded, then we can find a bound, and we can choose that bound to be a positive integer by increasing it if necessary, and we denoted that bound by kx. So this implies that x, by the definition of C, so this is in C kx. And obviously, this is a subset of the union. So any element in the space lies in the union, since the reverse inclusion is always valid. This implies that we can write our complete metric space X as a countable union of closed sets. By the corollary to the Baire category theorem, we can find an index k naught, okay, such that the interior of ck naught is non-empty. Okay, so let us take an element, say x naught. Since the interior is open, by the definition of the metric topology, there must be some epsilon such that the ball in X, centered at X naught with radius epsilon, lies entirely in the interior. So therefore, according to our definition of CK naught, f of x must be, the norm of it must be less than k naught for all x in the open ball and for all f in C. And you could easily establish this by applying this definition here and replacing k by k naught. So if x is in this ball, therefore it is in ck naught, and therefore the image must be less or equal to k naught. And this ends the proof. Why? You can just take, since this is true for any x in this open ball and any f in this collection C, you can then take the supremum over all f in C and then the supremum over x in the open ball, and then that would imply that the supremum is less or equal to k naught, therefore it is finite. So that's the proof of the uniform boundedness principle. Again, a collection of pointwise bounded functions that are continuous from a complete metric space X into a norm vector space Y is necessarily uniformly bounded over some open ball. And we can use the uniform boundedness principle to establish the Banach-Steinhaus theorem. It is sometimes called the resonance theorem, for instance, in the book of Ucida. This Banach-Steinhaus theorem or resonance theorem can be, let's say, utilized in the study of stability of infinite dimensional ODEs, linear ODEs. So for instance, you can think of the heat or the wave equation, the linear heat and the linear wave equation. You write that as an abstract ODE in some function space, and stability can be derived using this Banach-Steinhaus theorem, of course, along with some other results. So that's the significance of this. This can be applied in the stability theory for linear time invariant systems, in particular for infinite dimensions. So again, we suppose that we have a Banach space Y or a Banach space X. So this is a particular complete metric space, and Y a norm vector space. So the metric is now induced by a norm. And C is a sub-collection of the space of linear operators, linear and bounded operators from X to Y. Then, okay, denoting the operators in C by T. If you have a pointwise boundedness, in other words, this supremum is finite for all T, or I should say for all X in capital X, then this collection of operators, okay, although they have finite operator norms, the operator norms will not explode. In other words, the supremum is also bounded with respect to the operator norms. So pointwise boundedness implies uniform boundedness with respect to the operator norm. So without going into the technical details at first, take note that the uniform boundedness principle implies only boundedness with respect to some ball. Okay. Since here we now have a linear structure or vector space structure in X and in Y, we can do translation. So we can translate that ball into a ball centered at the origin, and we can scale that by homogeneity, and with that we can obtain this theorem. So that's the main idea. So going into the details, okay. Since a Banach space is complete metric space, we can apply the uniform boundedness principle. Okay. So by the uniform boundedness principle, there exists an X naught, X, and let's say what? An epsilon, an M, both are positive, such that the supremum of this over all X in this open ball and over all T in your collection C, the supremum is bounded, therefore this must be less or equal to some constant, say M, for all pair X and T in this open ball and in collection C. Okay. So we, in this case, we have only rewritten, I should say, the conclusion in terms of the supremum in this way. So if I take an element Z in this open ball, okay, then so we translate the ball to a center 0. We can write this as T of Z plus X naught by linearity, okay, minus T of X naught. Then you invoke the triangle inequality. Now you can see that, okay, since Z is in the ball centered at 0 with radius epsilon, If you translate that with x naught, this is now an element of this ball. And obviously x naught being the center is also an element of this open ball. Okay, since we have this, so replacing or applying this to z plus x naught and x naught, we get a bound which is twice of m. And this is true for any t in your collection C. Let us take a ball or an element of the Banach space X on the unit sphere. So this is the boundary of your closed unit ball. Then if you scale this by epsilon over 2, this is obviously in the open ball centered at 0 with radius epsilon. Because the norm of this will be epsilon over 2, that is less than epsilon. Okay. If I use this as my z here, okay, I know that the norm of t, epsilon over 2x, is less or equal to 2m, okay, for all t in C. Now applying the linearity of t and the homogeneity of the norm, if I multiply by 2 over epsilon both sides, so I should now have here 4m over epsilon. The epsilon over 2 on the right will be cancelled. And this is true for any x having a unit norm. Therefore, the sup over all t and c of the operator norm t, according to the definition of the operator norm, or more precisely, one of the definitions, equivalent definitions. So you have this. So we use the unit sphere as our definition for the operator norm. And this is less or equal to 4m over epsilon. So you just take the sup here with respect to x and then with respect to t. And obviously this is finite. And this implies a uniform boundedness of your collection C with respect to the operator norm or operator topology. That's the Banach-Steinhaus theorem. So if you can notice here, the main ingredients are the translation, because you have now a vector space structure, as well as scaling. So it's the translation part, and this is the scaling part. So the proof of the Banach-Steinhaus theorem relies on the uniform boundedness principle, and in turn, the uniform boundedness principle was derived from the Baire category theorem. In the next lecture, we will discuss another set of theorems that can be derived from the Baire category theorem, namely the open mapping theorem and the Sauerbitt's consequences as well.